Good morning, Dr. ZHUO and my fellow friend. Today, I'm going to present our project about the analysis of Parkinson disease. So, the Parkinson disease is a neurodegenerative disorder that affects millions of people while leading to a significant impact on their quality of life. So, the dataset we will be using include information of 2,105 patients. So, our wearables consist of age, gender, ethnicity, BMI, smoking status, alcohol consumptions, physical activity, diet quality, and so on. Okay, by analysis the dataset, we aim to identify the factors that contribute to the risk of Parkinson's disease and understand their relationships. This analysis will provide valuable insights into the health profiles and potential risk factor of patients, aiding in the prediction and management of Parkinson's disease. So our projects consist of 5 objectives. The first is determine the primary demographic, lifestyle, and so on. The second is evaluate the influence of lifestyle. Third, investigate the relationship between other medical conditions. And fourth, explore how various health metrics. And the last one is create statistical model.
Hi Dr. ZHUO, my name is Chang from section 10 and I'm going to explain about the two sample hypothesis tests in our report. So in this analysis, we will use variable called physical activity score and sex to test whether the mean physical activity score of male patient is different from the female patient at 95% of confidence level, which is 0.05 significance level. So we're going to assume the variance is unequal and unknown, and the physical activity score means the ability to move in daily life. So it's supposed to not have any inequality between male and female. And then we're going to use R programming to organize and calculate the frequency, mean, and standard deviation for the physical activity score for both male and female patients. After using R programming, we output the information, and here's the output. And I organize those information into the table. So here's the frequency of the male patient and the female patients. And here's the mean of the physical activity score for male patient and female patient. And this is the standard deviation of the physical activity score for male patient and female patients. And then I'm going to state the hypothesis statement. For the null hypothesis, the mean physical activity score of male patient is equal to the mean physical activity score of female patients. But for the alternative hypothesis, the mean of physical activity score of male patient is unequal to the mean physical activity score of female patients. And then here's the formula of the test statistic when the variance is unknown and unequal. Since in a null hypothesis, the mean physical activity score of male patient is equal to the mean physical activity score of female patients, so the difference is 0. And then here's the degree of freedom formula when the variance is unequal and unknown. And then we're going to apply those information into R programming, and we're going to get the results, which is the picture in here. So according to the R Studio calculations, the test statistic value is 0.1204196, and the degree of freedom is 2102. So after we get the degree of freedom, and also we have the significance value now, we are able to get the critical value from the table. Also, we can get it from the R programming. So the critical value is 1.961094. And after we get the value of test statistic and the critical value, we can make conclusion now. Since the value of the test statistic is 0.12 and the critical value is 1.96, the test statistic value is less than the critical value. So we failed to reject the null hypothesis. That is, at a 0.05 level of significance, we do not have strong evidence to conclude that the mean of physical activity score of male patient is different from the female patients. And here's a graph that you can see more detail about it. And then here's the means, the box plot that will show the mean of the female patient and also the male patient. You can see they're actually quite close between each other in a range. And then here's the dot plot. Same, you are able to see the mean value at what position. The red dot is the mean. You can see they're actually at a quite similar position.
So, hi Dr. ZHUO, I'm HENG and I do the correlation test in PSDA project 2. So, in this analysis, we will use variable alcohol consumption and cholesterol total to determine there's a linear relationship between alcohol consumption and total cholesterol levels of our patients at a 95% confidence level using this method, Pearson's product moment correlation coefficient. So because of both of these variables is ratio type, so I choose to use Pearson product moment correlation coefficient methods. So this is the relationship between alcohol consumption and total cholesterol levels. So alcohol consumption is between 0 to 20, and this is total cholesterol is between 150 to 300. So this range is based on our data. So basically this scatter plot, I use RStudio to produce it. I can show the code here. So this is my code. Yeah, so this is my code to show this relationship between alcohol consumption and total cholesterol. Okay, so basically if we just observe with our eyes, so you can see actually this data almost don't have any outliers. So because of these methods, the method we are using, this Pearson product moment correlation coefficient method, is very sensitive with the outlier. So basically I think our data don't have any outliers that will make a big effect in our calculation. So after that, I calculate the sample correlation coefficient R by using this method. So this is the result that produced in my R here. Yes, here, as you can see here. Okay, so I have highlight here. So this is my R, sample correlation coefficient. So actually, based on this negative value, I know that this is a negative linear correlation, but this negative value are too far from -1, but very close to 0. So actually, this is a very weak linear, weak negative linear correlation relation between alcohol consumption and total cholesterol. Okay, so after that, I do test for correlation, and this is my hypothesis statement. Now hypothesis rho equal to 0, which means no linear correlation, and H1 is rho not equal to 0, which means linear correlation exists. After that, this is the formula that I use to calculate the test statistic. So I have highlight also, this is my test statistic. Okay, so by using RStudio, I get the test statistic T equal to negative 0.98102. After that, I want to find the critical value, and I know the alpha is 0.05, and my degree of freedom is n minus 2, 2103. So from the T table, since this is a two-tail test, so I have two critical value. One is the lower tail, and another one is the upper tail. So I have negative 1.96 and 1.96. So if my test statistic is larger than 1.96, or the test statistic is smaller than negative 1.96, we can reject the null hypothesis. Otherwise, we will fail to reject the null hypothesis. So this is the graph that I do. So actually you can see 1.96 is here and negative 1.96 is here. So the negative 0.98 is the test statistic. I get this purple one. So as you can see, it is in the empty region, which means not the shaded region, shaded by green color. So actually, this value is larger than negative 1.96 and smaller than 1.96. So unfortunately, we failed to reject the null hypothesis because we have no sufficient evidence to conclude there is a linear relationship between variable alcohol consumption and total cholesterol at 5% level of significance. So basically, this is the output from my RStudio. So I show here. So in conclusion, actually, according to the small r, the sample correlation coefficient I calculate is very, very weak negative linear correlation, which means the more alcohol consumption of the patient, the less total cholesterol of the patient. But what we get here in conclusion is there's no sufficient evidence to conclude that there's a linear relationship between variable alcohol consumption and total cholesterol at 5% level of significance. So unfortunately, we failed to reject the null hypothesis. So that's all for the correlation test. Thank you.
So I'm going to share with you the regression test that we have done for this analysis. So for the regression test, okay, 3.3, yeah, here. The regression test will take alcohol consumption and sleep quality with two two dependence variables. So we assume that the value of sleep quality is depending on the value of alcohol consumption or otherwise. So here is the scatter plot of alcohol consumption vs sleep quality. And here is the straight line. It is a linearly dependence. The relationship is linearly dependence. And here is the equation for the population linear regression. So now for this equation, it has B1 estimate of regression slope and B0 is estimate for regression intercept. So we want to find the value of both value of B1 and B0 first. And when after using RStudio and uh, we give RStudio the equation of this and it get the result of 68.1263 for B0 and 0.2889697 for B1. And now substitute back the value into the linear regression equation. Here is the estimate value of y. Okay. And after that, you want to find the r square, which is coefficient of determination. So before finding r square, we need to determine SSR and SST first, which means sum of square error and sum of the square and sum of the square regression. After finding the value of r square, we can know there is a 0.003% of variation in sleep quality is explained by the variation in alcohol consumption. And after that, we find the standard deviation of regression slope. Using RStudio, we get a value 0.0067. And after that, we want to do a t-test analysis to determine whether the alcohol consumption is related to the sleep quality or not. So we make a new hypothesis, which is B1 equals to 0, not linearly not linear relationship, and B1 is not equal to 0, linear relationship is exists. For finding the critical value, we use the significant level, which is 0.05, and the degree of freedom is 2103. So here is the test statistical value that we find from the RStudio is 0.2692. So here, so we assume that here, since this is a two-tailed test, so we assume that the t value that we find from the table is 1.96 and negative 1.96 for the degree of freedom 2103 and the two-tailed significant level 0.05. Since the value of the t statistic value is less than the critical value, so we can conclude that the sleep quality is not depends on the alcohol consumption, and we fail to fail to reject the new hypothesis that we make here. Okay, so yeah, from this summary linear regression model, we can obtain a value such as here. Here is the value that I had mentioned from the above side. So that's all for me. Thank you.
My name is Ali Hao. Today I'm going to talk about the chi-square goodness of fit test.
In our analysis of Parkinson disease dataset obtained from Kaggle, we aim to explore the distribution of the smoking category among the participants. Specifically, we conduct a chi-square goodness of fit test to determine whether the observed sequence of smoking status, smoker or non-smoker, significantly different from an expected uniform distribution. So our null hypothesis is the observed frequency of the smoking category follow a uniform distribution, meaning each category has an equal probability of occurrence. Alternative hypothesis is the observed frequency of the smoking category do not follow a uniform distribution. So this is the result. So our chi-square is 348.91. This value represents the magnitude of the difference between the observed frequency and the expected frequency under the null hypothesis. The degree of freedom for this test is 1, which corresponds to the number of category minus 1. In this case, two category, smoker and non-smoker, 2 minus 1. So df equal to 1. The p-value is extremely small, less than this one, which is far below the common significance level of 0.05. Hence, we reject the null hypothesis, suggesting that the distribution of the smoking status among participants in the Parkinson's disease dataset is not uniform. This finding implies the presence of significant bias or patterns in smoking habits among the study participants. The histogram further insulates this division, underscoring the need for deeper investigation into how smoking behavior may correlate with Parkinson's disease outcome within this dataset. So now I will show the code to produce the result and the histogram. We open our R. So you can see the result here and the histogram here based on the code. So I think that's all.
And then I'm going to explain about the chi-square test for independence in our report. In this analysis, we will use variables called rigidity and bradykinase symptoms, where we will test whether those two symptoms are independent to each other or not at 95% of confidence level, which is 0.05 significance level. And then we are going to use R programming to organize, generate, and calculate two-way contingency table of rigidity symptoms and bradykinase symptoms. So after using R programming, we display the table. So here's the output, and I organize those information into a table to make it more easier to understand. This is also a two-way contingency table, and then we're going to state the hypothesis statement. So for the null hypothesis, the rigidity and the bradykinase symptom are independent to each other. But for the alternative hypothesis, the rigidity and the bradykinase symptoms are dependent to each other. And then we have to find the critical value. Given that we have 95% of confidence level, so the significance level is 0.05, and for the degree of freedom, there's a formula for the chi-square test for independence, which is the number of rows in the two-way contingency table minus 1 multiplied with the number of columns minus 1. So based on that formula, we can get that our degree of freedom in this test is equal to 1. Since we have value of significance level and the value of degree of freedom, the critical value we can find in the chi-square table, or you can find it in R programming. So the critical value is 3.841. After that, we can find the test statistic value now. So before we get the test statistic value, we have to find the expected count for each cell. After we get the value of expected count, we can find the test statistic value. So the value of test statistic is 3.6454. And since we have the value of test statistic and the value of critical value, we can make decision now. So besides of that, the p-value is also 0.05617, which is more than 0.05. And the test statistic value is 3.6454, which is less than the critical value, 3.841, and the test statistic is not in a critical region right here, so we fail to reject the null hypothesis. And we can conclude that we does not have strong evidence to say that the rigidity and the bradykinesia symptoms are dependent to each other. And that's all of our explanation. Thank you.
In conclusion, our comprehensive statistical analysis of Parkinson's disease dataset in both 2,105 patients has provided several significant insights into the factor affecting the risk and progression of the disease. Firstly, our two-sample hypothesis indicate no significant difference in physical activity level between male and female patients, implying gender does not influence this aspect among Parkinson's disease sufferers. Moving to correlation, our analysis revealed a negative correlation between alcohol consumption and total cholesterol level, which are equals to negative 0.02138736. This suggests that change in alcohol consumption do not predict variation in total cholesterol level among Parkinson's disease patients, leading us to fail to reject the null hypothesis. For the regression test, we found that the value of sleep quality does not depend on the value of alcohol consumption, as indicated by our regression model, y hat equals to 6.9785 plus 0.0018x. The linear relationship between these variables was insignificant, leading us to fail to reject the null hypothesis. In reality, this suggests that other factors might be more influential on sleep quality among patients. Lastly, our chi-square test of independency show rigidity and bradykinesia symptoms occur independently of each other, indicating they may manifest through distinct physiology mechanisms in Parkinson's disease progress. However, our chi-square goodness of fit test revealed a significant deviation from a uniform distribution in smoking status among participants. The observed frequency of smoker and non-smokers significantly different from what would be expected by change, leading us to reject the null hypothesis. This finding highlights a notable bias or patterns in smoking habits within the study population, suggesting the potential influence for smoking behavior on Parkinson's disease risk. In summary, our analysis suggests that gender does not impact physical activity level. Alcohol consumption has little effect on total cholesterol, and rigidity and bradykinesia symptoms occur independently. However, smoking habits show a significant patterns indicating a potential risk factor for Parkinson's disease. This project has enhanced our data analysis skill using RStudio and provide valuable insight into Parkinson's disease. Aiding in future research and intervention strategy, we extend our special thanks to our lecturer, Dr. ZHUO, for his guidance throughout this project. Thank you.